you here in the third day of this and FDP program, Machine Learning Based to Beyond. Now with us, Dr. Anup Nandi sir is with us. Uh, Dr. Anup Nandi is active with the Department of Computer Science and Engineering, National Institute of Technology, Rourkela. He served as a professor in charge in Center of Industrial Automation and Robotics at National Institute of Technology, Rourkela. He also served as a member of Intellectual Property and Innovation Center at National Institute of Technology, Rourkela. His area of interest includes artificial intelligence in healthcare applications, computing human cognitions with EEG signal analysis, human robot interaction with gesture, speech and emotion, and human gait analysis with deep learning techniques. He received an early career research award from the SER, Government of India in the year 2017. He received the prestigious NVIDIA GPU Grant Award in the year 2018 for his research on deep learning techniques in healthcare applications. He was selected as Indian Young Scientist in the thematic area of intelligence to participate in 5th BRICS Conclave 2020 held at Chelyabinsk, Russia from September 21 to 25, 2020. Sir, he is a recipient of JSPS fellowship from the government of Japan in the year 2022. Among many, he has completed two bilateral projects funded by JSPS Japan and DST Ministry of Science and ICT of the Republic of Korea in joint collaboration with Tokyo University of Agriculture and Technology and Seoul National University in the year 2019 and 2024 respectively. He is a senior member of IEEE. He has published a good number of research publications in reputed conferences and journals, namely IEEE Transaction on Neural Networks and Rehabilitation Engineering and IEEE Transaction on Cognitive and Development Systems. So I am thankful to Dr. Anup Nandi sir. Today he is with us and he will take all the 4 hour 2 session, the first session and the post the second session also. So thank you very much, sir. I hand over the session to Dr. Anup Nandi, sir. Now, please, sir.
Okay, sir. So thank you so much. First of all, I'd like to thank Dr. Surendra Hans for inviting me in this wonderful session for AIML. So I'll just take first half. I'll just cover two important things. That is a fundamental of base decisions rule and this k-nearest neighbor classifications algorithm. And in the second half, I'll just give these some hands-on sessions of this how these two things can be implemented using Python programming languages. And mostly we'll just talking about the satellite images. For this, how you would be able to do the classification of the satellite images by using these base decisions rules and this k-nearest neighbor. So now let me just start with this. So my screen is visible.
Yes, sir. Yes, sir.
And these slides are changing, sir.
Um, it is not in the full mode, full screen, sir. But now we can see, sir. And slides
But
are not changing.
I have done the full screen, sir.
Uh,
Sir,
no,
these slides are changing.
no, sir.
Sir, just a minute. Let me just stop again and again. Now, sir, can you just see the screen?
Yes, sir. Yes, sir.
And these slides are changing?
Yes, sir. Yes, changing. Yes, sir.
Okay. Okay. So now the topic that I have chosen, that is a fundamentals of mathematically, I would like to explain to you about this base decisions rule. And before giving this introduction to the base decision rule and its application, I just tell you about the fundamental of probability and statistics. As all of you know, that as this course has started with this mathematical jargons of probability and statistics, and what are the prerequisites to are required to understand the ML. But to reiterate it, I just wanted to tell you that in order to understand this ML part, you need to have a sort of knowledge of linear algebra. You have some sort of knowledge of this the probability and statistics, and also this calculus. Now, as this topic is concerned about this base decisions rule, so it is a probabilistic based classification technique. So now, in order to implement it or in order to understand it, so firstly, there is a two important things that we need to understand, that before understanding this probabilistic based classification technique, mainly this base decisions rule. So there are two cases for this classification, or more precisely, that is a supervised classification. First is class conditional probability density functions, that is to be known to you, and prior probability is also known to you. And second is training sample points are also given to you. So now each and every term that I'll just wanted to clarify. So there is a written that there is a class conditional probability density function. So now, before understanding the class conditional probability density function, we need to first understand what is a density function. Okay, so now in the density, there is a broad definition of the density that we have seen in the class 8 or 9. The density is equal to mass by volume. That we have already seen. But what is a probability density function? So any function is said to be a probability density function if it satisfies some properties. Okay, and what are these two properties? So that I'll explain to you. And but here it is written that is a class conditional, because whenever you are going to do some classifications problem, so we are assuming that the data sets are given for these particular classes. So whenever the data set is given for the particular classes, we are assuming this data has been drawn randomly, or taken from some particular populations with certain distribution. So now a density functions, whenever we are talking about the probability density function, we will be assuming that it will follow some particular distribution. So more precisely, that we would say that this distribution is a quasi-normal distribution or Gaussian distribution, which is more common. So now, what are the conditions to be satisfied to call a function is a call a probability density function? As you can say, a function that is called the fx, or we can write px, probability function of px, where x is in Rn, means here it is called this n-dimensional, that we would like to say that is a fx x, it is Rn, it's a n-dimensional Euclidean space. It's said to be probability density function if it satisfies two properties. What is the properties? Fx is greater than is equal to 0. Okay, so for all x that is belong to R, or I can more precisely I can write Rn also here, that is a some dimension is given. Okay, like if I'm going to have, this is a fx, so this x is a vector. So if I'm going to make x is a vector, so it has got small n components, x1 to x1 x2 x3 till xn. So these are the components are there, and this is if fx is greater than is equal to 0 for all x, and minus infinity to plus infinity, fx dx is equal to 1. It means that that is the area and that the curve is 1. So when I'm going to write x, so it is a vector, so it has got n components, so I can write fx1 fx1 dx1 is equal to 1, fx2 dx2 is equal to 1 till fx and dxn is equal to 1. So if any function which satisfies these two properties, we would say that this function is called a probability density function. So such type of functions is called a Gaussian function, or that is called the normal density function. So any function which satisfies these two property, that is called the probability density function. Now similarly, we'll have a function which satisfies which follows a triangular distribution. So I would say this I want to apply a density function with which follows the Gaussian distribution. Similarly, I can also apply the density function or probability density function which satisfies this triangular distribution. Now this, if you take the triangular distribution also, suppose it is obviously fx greater than is equal to 0 and area under the curve is equal to 1, that you can have half base into height. So these are the simple way. So I cannot use this any function which does not satisfy this density function. I mean, which does not satisfy these two properties. So this way that we could think of it, like whenever you are going to apply the base classification technique or base decisions rule. So we are going to have a density function or probability density function which follows certain distribution. So here we will be assuming the distribution is a multivariate Gaussian. So that I will be explaining to you. So now this is a now second thing is that is called the prior probability. Prior probabilities are known. So what are the prior probabilities? Suppose there are two classes are there. One is, suppose I am taking the example, one classes is this Indian community, another classes is called the Chinese community. Now you just mix them the two communities. Okay, and then you have a mixed distribution. From the mixed distribution, if you are going to take randomly 40% are Indian population and 60% are the Chinese population, then the prior probability for the first class, that is Indian class, will be 0.4, and the prior probability for the second class, that is Chinese community, that is called 0.6. So this way that this prior probability can be estimated. Or if it is not given to you, so you can estimate it from the training sample points also. So if your capital N, it is a number of samples is given, now you can draw randomly from the mixture density, then you can estimate for this first class one, there is a prior probability will be N1 by N. That way that I can write, or N2 by N, that is a prior probability for the second class. So this way that you can calculate. Okay. So now these two information will be given to you. And second is training samples points. As I'm going to solve the supervised classifications technique, so more precisely the training sample points will be given to you. Okay. Now here I already explained it. Now here this is a, now whenever we are going to using this set, that is a is a set, then Rn we are going to use, this is a not is a real space, not this imaginary space. So now in the real space, that is an n-dimensional real space, that the n-dimensional real space can be decomposed by R into R, where R it is a minus infinity to plus infinity, that the R square, that is a minus, this is a Cartesian product actually, yeah, minus infinity to infinity into minus infinity to infinity. Then it is R cube, then you will have minus infinity to infinity into, so this way that you can extend it. So if it is an Rn, n-dimensional real space, so you have Cartesian product of all the sets. So that way we can understand. So this is a more commonly used normal distribution. So this normal distribution, that is X, it is a vector, it is a n, and it has got two parameter, mu and sigma square. Mu is a mean, and sigma square, it is a variance, so which follows a mean and variance. So now if this, there is a two things. One is that this distribution is given. If the distribution is, we are assuming that, so your data is following this particular distribution X. Now if this distribution is not given, you can also estimate the distribution, or you can also estimate the density function from this given training data points. Okay. So there are different techniques to calculate it. Now its probability density function that I can have, there is a 1 by, this very common formula, 1 by root over 2 pi 1 by sigma x p of minus of x minus mu by sigma square. So this way that we used to calculate, where the range of x, mu and sigma is already given, and if you have changes, so if you just plot it, then you can have the different type of different shape that you would like to have. So this is a commonly used normal distribution. Now there is an exponential distribution, because why I'm explaining to you that you could take this density function which follows some certain distribution, and this is a typical architecture of or these characteristics of the exponential distribution, that is a e to the power of minus x and theta e to the power minus theta x. So there is a binomial distribution, Cauchy distribution, gamma distribution, beta distribution. So many distributions are already available, and then you can check it for as per your requirement, that the data set that you are going to use, which follows which type of distribution. Then accordingly you just fit it. Then you can pick up for the further processing. So now there is some proof is given, that is a for this normal distribution, that how these things is being, I mean, there's a mu and this is a mu and variances, how it is be calculated, and there is a proof is there, that is there's a how we are going to calculate this expected mean or the expected variances. So this proof is already given. When I'll share this PPT, you just check it. So now today my for this today's topic, so I'll be using this probability density function, which follows a multivariate Gaussian distribution, Now how it looks like? Now the distribution, that is a mu as it is a multivariate and we are not using it as a single variable, you are going to use some multiple variables for your case. So now this is a mu. So mu is a vector, it is a mean vector, and this is a sigma. What is a sigma? Sigma is called this covariance matrix. I hope that you had a course of this fundamentals of this statistics course, and that you have already acquainted with this term. What is the mean, how the mean can be calculated, how this covariance can be calculated, what is the formula of the covariance, what is covariance matrix. I'm assuming that you are having this idea of these things. So now this multivariate distribution, so how it looks like, what is the formula? That I can write this: if fx is equal to 1 by root over 2 pi to the power m, determinant of sigma to the power half, exp of minus half, x is a mean vector, okay, minus mu is also a mean vector, and this is a transpose, and this is a sigma inverse. This is a variance covariance matrix, or we would say this is a covariance matrix. It is a variance covariance matrix. This is called also this dispersion matrix. So there are several names of this thing, and this is a x minus mu. Okay, now we would say why do we use this multivariate Gaussian distribution? Because this function also follow, it is a density function, that is a probability density function. If it is you follow this probability density function, so it must satisfy these two properties. What is this properties? Fx is greater than or equal to 0, and integration minus infinity to plus infinity fx ds is equal to 1. Now we'll just prove it. Now you see that's determinant of sigma. So this is a constant term. Now as you can see, this is a determinant of sigma. It cannot be always uh, positive. So determinant of sigma cannot be always positive. It can be negative and also 0. Now if it is negative, then this will have a complex things, so complex number, so we are not going to use it. So as per the definition of this density function, it will not allow. Now if it is 0, then whole things, the 1 by 0, the whole things should be undefined. So this determinant of sigma cannot be negative, not be 0. So the determinant of sigma must be is greater than 0. Okay, now we'll prove this one. Now as we can see, this is a x minus mu transpose. So x is a column vector, and it has got n components. Mu is also a column vector, and it has got also the n component. Now whenever you are going to have the transpose, so it is a row vector. Now if it is a row vector, then you will have this dimension. What should be the dimension? This dimension will be 1 cross 1 cross 1 cross m. Okay, so this is a row vector. Now this x minus mu, so x is a column vector and mu is also a column vector. Now it should be this n cross, you have this n cross 1, you have this n cross 1, correct? And this is a square matrix, this is a variance covariance matrix, this is a square matrix or dispersion matrix. Now its dimension will be n cross n, n cross n, that we are going to write. Now as you can see, now you just multiply it, 1 cross n multiplied by n cross n, you are going to have 1 cross n. Now 1 cross n again multiplied by n cross 1, you will get 1 cross 1. This is a scalar quantity, correct? Now this is a scalar quantity. Then anything exponential to the power anything will be a positive quantity. So now this has to be a strictly positive. So obviously the function that we are going to use here, so it is actually a density function, because it is fx is greater than or equal to 0. And if you also do the integration, then you would say this area under the curve is also 1. Okay, now this inverse, it is a non-singular matrix. Then this determinant of these things, it is a non-zero, because if it is a singular, then you cannot find the inverse. So it has to be a non-singular, and it is strictly positive definite. So there is a property, so this matrix is called a strictly positive definite, or you can say this non-negative definite matrix. Okay, now you can easily find these eigenvalues and eigenvector for this strictly positive definite matrix. Okay, so this strictly positive definite matrix, so that you can have, that is a formula that for this strictly positive definite matrix, you can write, that is a transpose, you can write in this way, a transpose a it has suppose A into A, it has suppose A into A, if it is greater than is equal to greater than 0, so this is called the strictly positive. So A is a it should be a non-zero vector. Okay, so non-zero vector means all the components of this vector, it should not be 0. Okay, so it is a non-zero vector, it is also a non-zero vector, and it is a matrix. So this is called a positive definite matrix if it satisfies these two things. Now from this positive definite matrix, this variance covariance matrix, so that you are going to use for this case, it will follow this certain condition. Okay, so I'll be using this formula, multivariate Gaussian distribution, to use it for establishing this my base decisions rule. Okay, I'll just coming to the base decisions rule. So before that, the fundamental, I'll just quickly give it to this idea of this means what is the fundamental of this statistics portions or the probability portion, which is required to calculate this prior probability, posterior probability, and this likelihood function, all sort of things is required. So now nevertheless, so these features, so that you know already, so these are the measurable quantity that you can obtain from the patterns, and this classification task is based on the respective values that you know. So you need to have some mapping functions for doing these certain tasks, and these feature vectors that you can write it, this is a number of features x1 to xl, l dimensional feature vector, and this we used to write it as a column vector, or simply we can write it is a, when I make a column vector, it is a transpose, this is a row vector, and this it is known as a random vectors. And the objective of the classifier, it is a set of function and whose values you can compute it at a particular x, and your objective is to determine this class to which this corresponding pattern belongs. Okay, so that we'll see this, what are the class belongingness of the pattern. Your objective is to classify this test pattern, and you have to calculate these posterior probability values for that each classes, and wherever you are going to get the maximum one, then you would find that this pattern belongs to this particular class. This is called the naive Bayes rule. Based on this conditional probability values, you are going to take a decision, this class belongingness of the pattern based on this maximum a posterior probability values that we used to say. For these things, the condition is that all the features that you're going to have, that has to be independent. Okay, so this is the condition for the naive Bayes. This will also see the difference between naive Bayes rule and the Bayes decisions rules, and these are the standard technique for any classification systems. You have to first capture the data, then you have to analyze this data, generate these features, apply different techniques for selecting these features, design this classifier based on the feature vector, and then you have to test it based on the test pattern to evaluate the performance of your system. So these are the ways to say. And I think you know the difference between supervised and these unsupervised techniques, where this pattern whose class is known a priori are used for the training, and unsupervised this number of classes unknown, and no training patterns are this available. So these are the basic things that it is required, that I already explained this part, and how we are going to represent a vector, because whenever you are going to use some techniques for this feature representation, you need to represent this feature in terms of this feature vector. And for these things, so you need to have representatives, that is if you have these two vectors, suppose if it is a is my height of the features, and this is a weight features for these n persons, that you can write it a1 to n and b1 to bn. So this way that you can calculate it. So this already explained. Now these basis of statistics, that suppose how we are going to calculate this mean. So if you are going to have these n observations from x1 to xn, and the mean can be calculated by x bar is equal to 1 by n, I is equal to 1 to xi. So now how this mean can be calculated? So there is a way techniques to calculate. Suppose you just see that x1 to xn, these are the observations are taken from some population, and I am going to estimate this, trying to find the functions uh, to find the difference between, that is a all the observations to a. So that is fa is equal to 1 to a xi minus a whole square. So this is why I'm going to have this square term. I'm trying to make the differences. If somehow this difference is negative, then I can use this as a square term, so that it can be positive value, where a is also a point that is belongs to what. Now this function, so how we are going to find the mean, that I am trying to tell you. Now if I'm going to have this function, I have designed this function in such a way so that I can estimate this mean, okay, from my actual population mean. So now this is a this function, if you just differentiate it, now I'm trying to find the minimum values of a such that this entire things will be minimized. For what values of a this function is minimized, so I need to do this minimizations with I need to do this differentiation with respect to a. Now if you do the differentiation, that I would have, that is a is equal to uh, 1 by n, I is equal to 1 to xi. So this 1 by n, I is equal to 1 to xi, it is a nothing but a x bar that you have already calculated. Now this mean of this function occurs when you are going to have this minimum values of x, when a is equal to xi. So this is just a simple way to understand it. Now if you just replace a with x, then you can easily find the variances. If x is equal to simply just xi minus x bar square, or you can have this 1 by n also, because you are doing this averaging for all the samples. So this is the formula for the variances. So from where it is coming of the formula of the variances, when you are going to calculate a mean, and you have to minimize this is a this for this function, and for a particular points this function is going to minimize, and this function, that is nothing but we have already calculated, and this variance is a 1 by n is equal to 1 to n xi minus x by 1. So we have already seen this formula, and this is a concept of probability that we have already seen. That is a you have a random variable x, and whenever you are going to have the random variable x, our x1 to xn, all are called the independent and identically distributed random variables, or we can say this is a random vector. So this is it whenever you are going to have this random variable, it satisfies this very unique property IID, independent and identically distributed random vector, okay. And with this probability p1 p2 p3, so then this mean of the random variable that you can calculate, that is ex is equal to expectation of x, that is I is equal to 1 to infinity xi into pi. So this way that you can calculate this expected expectation of x, because if it is a discrete, if you are going to have the discrete random variable, then you are going to have the summation. If you have the continuous, then obviously you are going to have the integration. So that is a very common thing that we know everyone. Now this is independent and identically distributed. This is a random variable. So this is very, very important that you can refer any book. The definition is given. So now I'm just skipping this part. Now before because here in this formula you have seen there is a sigma was used. This is a variance covariance matrix. So now what is a variance covariance matrix? So before understanding the variance covariance matrix, you need to first understand what is a covariance. Now what is a covariance? Now covariance, suppose you have two variable x and y, and you need to find the relations between these two variables, that is called the covariance. Now I am going to have the sample points xi and yi. Now what is xi and yi? Suppose I am having these two features, okay. One is called my feature is height of a person and weight of a person. So these are the two features so that I am calculating, and using these two features, as you can say, x and y. X is my height and y is my weight, and from the in observation, now you just simply plot these features in the two-dimensional plane. Now I am trying to find the relationship between x and y on the basis of the sample point. Now you can have the many plots, you can have this many plot, and your objective is to estimate the mean of the population on the basis of the mean of the sample. Now I am going to show you these three different plots. So this is plot 1, this is case 1, this is plot 2, this is case 2, and this is another plot, this is case 3. As you can see, you just see first this axis, x axis and y axis. Now there is some points over there. Now if you just, what is the pattern of this point? When the x values is increasing, is y values is more or less increasing. As you can see from this case 1, when x values is increasing, is y values is more or less increasing. Now I would like to denote the relationship between this x and y by is greater than 0, means positive relationship. Why positive relationships? So I need to find the quantity. I need to find the quantity to find the relationship between x and 1. And this quantity, based on the characteristics of this pattern, this quantity is a positive quantity. Whereas On the other side, if you see in the case 2, when x values is increasing, its y value is decreasing. So now I would like to denote I would like to find a quantity which will denote the relationship between x and y. And based on the pattern of this data, so this quantity is a negative. I mean negative quantity. That is this relationship. It is a less than 0. Now, whereas in the third case, if you just look at closely, that all the points are more or less are equally distributed. Means there is no changes wherever any x values or y values are more or less this is the same. So now I would like to find the relationship with this equal. Okay, so there is no changes are observed. So these are the things. Now you can find the mean. So you can find the mean of these all the data points. So your mean will be somehow here. I have already denoted by this arrow. That is a x bar into y bar. So that is a mean of this data point. And here also this mean of the data points x bar and y bar. Here also this mean of the data point is also a x bar into y bar. Now what I am going to do, I am going to change my axis. So this was my origin 0 0. I mean it was my origin 0 0. Now I am going to shift my axis from 0 0 to x bar comma y bar for all the cases. So 0 0 to x bar comma y bar. So this is my new axis. I mean new origin. Now and from this new origin I am going to draw this line. Then I am going to have the axis is going to be shifted from x to x dash and y to y dash. So this is my new axis. Now if you look at this new axis on the new origin, you see there is some data points here. Okay, and these data points, and this is a positive quadrant, this is second, this is my first quadrant, this is second quadrant, this is third quadrant, and this is a fourth quadrant. Now if you just closely look at this first quadrant, now I'm taking this value. Okay, now I'm just going to draw this value. Now for this point, so this is this x values and this is this y values. Now for this all this point I can get this x values. For all the points I can get this x values and y values. Okay, now you just multiply the new x values and new y values. You just multiply the new x values. Now this is my new x values, so this will be my new x values for this point, and this is my new y values. Now for this point my new x values will be this and this y value. So you just multiply these both new x values and y values. Now whenever I'm going to do this multiplication, so now as this quadrant is a positive quadrant, okay, then this x value is positive, y value is positive, and their multiplication, whenever you're going to do the multiplication, so the multiplication is also this positive, and it is not only positive, its value is also large. Now on the other hand, in the negative quadrant, I mean third quadrant, this x values is negative. Okay, so this is the x values, and y values is also negative. But if you are going to do the multiplication, then this you are going to have the positive values. Okay, now if you look at the first quadrant, you have, and the third quadrant, you have more positive samples, as the product is as their product is positive. Okay, and they are not only positive, they are also large. Then these more positive samples, okay, or this more positive product value is going to dominate these less negative samples or the less negative product values from second quadrant and fourth quadrant. That's why this relationship is called a positive relationship. Okay, similarly in this second case, if you can see that in this second quadrant and the fourth quadrant, you are going to have your this more negative samples, or the product is negative. For the here is a product is negative, and you are going to have this maximum negative product. Here also have the maximum negative product, rather than this first quadrant and the third quadrant. So that's why, so these more negative points is going to dominate this less positive points. So that's why this relationship is called this negative relationship. Whereas in this third case, as you can see, for all the points, so there I mean these coordinate values, as you can see, their x values and y values is not changing, more or less same. Then this relationship is a equally distributed. So that's why it is a equally distributed relationship, and it is close to 0, or it is a equal relationship. So now now I can find now how we are going to interpret this relationship. It is nothing but a covariance. So this is a formula for this covariance. So now how it is coming? That is a I is equal to 120 xi minus x bar. Now xi minus x bar, it is a nothing but there is a shifting. So this is a this you are going to find this is a point from the origin from this point. This is x values. What is the x values? So this is a from x bar x minus x bar multiplied by y minus y bar. So that is already written. X1, if you are going to n data points, x1 minus x bar into y1 minus y bar plus x2 minus x bar plus into y1 minus y bar plus x3 minus x bar into y3 minus y bar. That way that you can calculate. This is a nothing but a covariance formula of the covariance. Now what is a covariance matrix then? This is a because your sigma is your, so your covariance matrix, it is a nothing but this is a one fat matrix that you can have. It is a n cross you can have this covariance matrix. It is a n cross n, and you can have cov of you can have this cov of, suppose I'm going to write this is a covariance of what I should write, x1 comma x1. So first is I can write this is x1 comma x1 comma I can write x1 comma x1 for the first one. First one I can write x1 comma x1. For the second one I can write x1 comma x2. Third one I can write x1 comma xn. Okay. In the second row I can write COB of x2 comma x1, then COB of x2 comma x2. Then here I can write COB of x2 comma x. And then finally you can have in the last column, in the last row, you can have last row in the last column COB of, I can write COB of xn comma, I can write COB of this is I can write xn comma COB of xn comma I can write that is a xn. So these are the formula for calculating this is a covariance matrix, and all the diagonal elements that you are going to calculate, COB of x1 comma x1, COB of x2 comma x2, COB of x3 comma x3, COB xn comma xn, these are called these variances. So the formula that you have already seen. Okay, that is the fundamental things, and it is required to calculate this is a covariance matrix. And this covariance matrix that we used to denote is by that is a we are going to denote this covariance matrix by sigma. So as you can see, we are going to denote it by this is sigma. And from this things, that is a correlation coefficient that you can calculate Rx is equal to COB of x comma y. This is a variance of x into variance of y that you can easily calculate. Okay, so this is a nothing but so, and or you can simply have the dot product between these two vectors. This I mean there's a proof of the Cauchy-Schwarz inequality. So this angle between these two vectors, or simply you can have the dot product, take the dot product, or that is a x1 minus x1 into y1 minus y bar. You can do the dot product. That is a nothing but a cos theta. You can find this way to calculate it. So now these are the very good remarks. That is in the covariance matrix, it has got the dispersion matrix, it has got the symmetric matrix, it has got this covariance matrix. Some important properties, and all eigenvalues should be greater than 0, and the determinant of this matrix, that is that that is a product of the eigenvalues. Okay, and eigenvalues and eigenvectors are only for the square matrix. And if you now how do you ensure it that the covariance matrix that you have calculated it is correct? What you have to do, you have to calculate if the sum of the eigenvalues is equal, if the sum of the eigenvalues is equal the sum of the variances, then the covariance matrix is correct. Because from the covariance matrix you have to calculate these eigenvalues and eigenvector. Now these eigenvectors, all the diagonal elements is called the eigenvalues. Okay, now if you just sum up this all the eigenvalues, now if you sum up all the eigenvalues and you sum up all the variances, now if both are equal, if sum of the eigenvalues is equal to the sum of the variances, then your covariance matrix is correct. So this is the fundamental thing. So now I'll just tell you this how the Bayes decisions rule can also be understood. So this is a this statistical proper nature of the feature vector x1 to xl I already explained. Now you have to assign a pattern represented by the feature vector x to the most probable of the available classes. Now you are going to have this m number of classes, that is w1 to wm. So you are going to have this m number of classes. W1 is first class, W2 second class, W3 third class, wm. Now you are going to find these probability values. That is simply a posterior probability, or we can say here also the conditional probability. That is a, what is the belonging, this is a belongingness of the x. So this is a test pattern belonging class. If you have m classes for each class 1 to class m, you are trying to find the probability values or class belongingness of this pattern for this corresponding pattern, the x. Now wherever it will give this maximum probability values, then you are going to take the decision that this pattern is belong to this particular class. So I can calculate pw1 given x, you are going to have this one probability value. Then I can calculate pw2 given x, you are going to get this another probability values. Then pw3 till pwm, so you are going to have the m number of probabilities. Now out of the m number of probabilities, which one is the maximum probability value? Okay, now which one is this maximum probability, that you can just denote it. Then you just classify or just find this pattern, assign this pattern to this particular class. So this is a very simple way of doing this thing, and we used to do it for the naive Bayes classification technique. That is a, here we are assuming that this all the patterns are, that is you are going to have, this is independent. So now you have to compute this a posteriori probabilities, assuming that that is you are known with these two important things. One is class conditional probability density function. Second one is prior probability. The two things are known to you. Now this prior probability that you know already, that is denoted by, prior probability is denoted by the capital P, as you can see. Pw1 means prior probability for the first class. Pw2 prior probability for the second class. Pwm, that is a prior probability for this, that is a mth class. And this is called a px given I. This is a density function, probability density function, or class conditional probability. Why it is called the class conditional probability density function? Because I can calculate px given w1 means first class. Then if you are going to have the m class, then you have to calculate px given w2 till px given wm. That's why it is called the class conditional probability density function. Why it is called the probability density function? Because it satisfies some property, and also it follows a multivariate Gaussian distribution. That's what it is called. Sometimes this is also known as a, this density function is called a likelihood function of x with respect to wi. These are the different names. And whenever you are going to apply the Bayes rule for m is equal to 2, then what is the Bayes rule? That is, I can write p of x into p of wix is equal to p of x given wi into p of wi. So it is nothing but it is p of wix. So these are this very common formula, that is a Bayes theorem. From the Bayes theorem you can already seen, this is a p wi given, this is called this posterior probability is equal to, that is a likelihood multiplied, this is called the likelihood multiplied by prior divided by evidence. Now this p of x, it is this common for all the classes. If you are going to solve two class classifications problem, now this px, this denominator part will be same for both the classes. So that's why we are not considering this denominator part while establishing this rule. We are only considering these two components. One is called this likelihood function, another is called this prior. Now this Bayes classifications rule for class m is equal to 2, you can see there's a given x, you have to classify according to the rule. So now you need to take a decisions. Now this x is belongs to w1 if it satisfies this condition. What is the condition? Is p of w1 x is greater than p of w2 x, then x belongs to class 1 or w1. Or if pw2 given x, if it is greater than pw1x, then x is w2. Now equivalent to, we can classify x according to the Bayes rule, that is a, or I can, these things can also be decomposed. Pw2x is nothing but, so it is a posterior probability. So this posterior probability I can write it by a likelihood function Px given W1 multiplied by prior greater than or less than based on the in which class you are going to classify this pattern, that is Px W2 given W2. Now if you are going to use the equiprobable classes, so what is the meaning of the equiprobable classes? Because all the classes, the prior probabilities are equal. If you are going to solve two class classifications problem, then prior probability for the first class is 0.5 or half, and prior probability for the second class is 0.5 or half. If you are going to write down this half also, then this half will be cancelled out from both this inequality. So that's why for the equiprobability classes, we are only considering this. This is a density function or likelihood function. So now you need to draw to understand it pictorially. Suppose I can draw the density curve. So now here the density function has been drawn taking into consideration only one features, because if I'm going to have these two features, so it will be in the 3D, so then I cannot draw here. So that's why we are going to use only this one feature, so that is an x. As you can see, x is a features, and I am just going to draw that is a density function, that is a px given w. So this is a density function for the first class, and this is a density function for this second class. Now it is generated by pxw1 for the first class and pxw2, this is second one. Now you need to take a decision. Now this is the intersection region, and this is here, it is a threshold, that is a x0. Now if so your objective, so there is an your objective is to find a classifier, okay, with minimum classification error. Okay, your objective is to minimize this class, that is a misclassification error rate. So your objective is to minimize this misclassification error probability, or minimizing this classification error probability. Okay, and this base classification rule is called the optimal with respect to minimizing the classification error probability. Now as you can see in the dotted line, that is the x0. Okay, as you can see in the dotted line, x0, it is a threshold. So it's partitioning the feature space into two halves, or two region R1 and R2. So according to the base rule, that for all values of xi in R1, the classifier decides W1, for all values of xi in R2, the classifier is decide W2. Now whenever it is going to decide it, then these are the shaded area. Now this shaded region, that is an errors are unavoidable, you cannot avoid this error. Now R1 region of the feature space, and we decide in favor of W1. Then R2 region of feature space, we decide in favor of W2. Now what you have to do now, thereafter there is a some finite probability for an x. So there is a some finite probabilities for an x which belongs to, or which will lie in the R2 region, and at the same time there is a some finite probability of x which also belong to the W2. So try to understand here. So there is a some finite probabilities for an x to lie in the R2 region, that as you can see in the R2 region, and at the same time it is also belong to the class W1. So that is an error. So if the points actually belong to class W1 but it is classified in W2, so there is an error. And or on the other way, the points is actually belong to W1 but it is classified in W2, so there is another error. So there are two types of error. Then we have to take a decision, it is an error. Now the same is true for the points originating from the class W2 also. Okay, now what is your objective? So your objective is to minimizing this classification error probabilities. So now this probability of error, that is a simply total shaded area. As you can see, that is a P of E is equal to minus infinity to x0. As you can see, this entire region R1 R2 is minus infinity to plus infinity, this minus infinity to plus infinity. Now minus infinity to x0, it is R1 region, then x0 to plus infinity, so it is an R2 region. So this, just look at this figure. Now this x belongs to R1. Okay, then if it is, then x in W1, if x classified in R2, then it x in W2. So but this classifier is optimal with respect to minimization of the classification error probability. Now base classifier is optimal, as I already told you, with respect to minimizing this classification error probability. so that this minimizes, or that you can have this threshold. So if you just changing the threshold away from x naught, it is always incurring some errors, and that corresponding this shaded area under this curve, so that you can find. So your objective is to, so I have already calculated this error. This is a total error. So this error is being calculated, okay, for finding. So what I should write? So this error that calculated, it is one type of error. So actually belong to this R2, but it is actually belongs to this R1, but it is classified in this W2. It is actually belong to R2, but it is classified in W1. So it is one type of error. So this, your objective is to minimizing this error. Okay. So now here, if you just, as I already explained to you, this therefore, if you just moving the threshold away from x naught, it always incurs the corresponding shaded area under the curves. Okay. So now you can just changing this threshold, and you can just calculating this error, and finally you can end up with the, what is the total error that you can calculate. Now here we are assuming this, that all the weights of the error are equal, but it is not necessarily true that all the time these weights of the errors are equal. Now when the weights of the errors are equal, then you can go for this minimizing this classification of error probability. But when the weights are not equal, okay, then your objective, then you need to find, there is a called the loss function that you have to do. Okay, in this case, what you have to do, you have to find this minimizing this average risk. Now the classifier error probability, that as I already told you, is not always the best criteria to be adapted for minimizing, because it assign that some same importance to all the errors. Because when it is the same importance, because when you are going to assign the same weight, okay, for this same weight value for this each error, but it is not possible on the time. So there are some cases in which there are some wrong decisions will have some serious implications. Now if you take the example of these medical applications, suppose it is much more serious that for a doctor to make a wrong decision that whether a tumor is a malignant or it is a non-malignant or benign. Okay, and then to be diagnosed by the doctor. Now if a doctor to make a wrong decision and a malignant tumor to be diagnosed by a benign one, or on the other way around, then if a benign tumor is diagnosed as a malignant one, then the wrong decision will be just cleared out using this subsequent clinical trial. But the first one, if this tumor is actually this malignant, but it is treated as a non-malignant, then there is a problem. Then now try to understand that here, if you are going to assign this equal error or equal weights of the errors, then there is a problem. Then what you have to do, you have to use some penalty term. So for each wrong decision, a penalty term is assigned, since some decisions are more sensitive than these others. So for two classes in these penalty terms, in such cases, it is more appropriate to assign a penalty term to weight this each error. Now for the W1, this is a class of, I can say two classes for the W1 class. For this is a class of the malignant tumor. For the W2, that is a class of this benign one. Now we are going to have the two regions, R1 and R2 regions of the feature space, and we decide this R1 and R2. R1 feature space we can decide in favor of W1. R2 feature space we can decide in favor of W2. Now here the loss matrix I can have, this is a, suppose this term is error, because if you know the confusion matrix that I already told you, so this if you have two class classifications, probably if you have seen the confusion matrix, now this diagonal element that you can see, this is a correct one. So this one means if you are going to two class, this pattern is actually belong to class 1, it is classified in class 2. Here in this pattern is actually belong to class 1, it's classified in class 2. This is an error. Here pattern is actually belong to class 2, classified in class 1. There's an error. So these are the two errors. Now you need to give some weight. You have to give some penalty term. That more penalty term, that if you are going to leading to this more error, okay, and less error, then less penalty term, that you can also design in this way. Now this lambda 1 2 penalty term for deciding the class W2, and the also the pattern belongs to the W1. Okay, and this risk for these things, here you have to calculate. This is a cost. There is a two things. One is called the cost of the misclassification, and this is called this. There is a error of the misclassification. When we can have the error of the misclassification, when both will have the equal error, equal weights. And the cost of the misclassification means you are going to incorporate some penalty term. Here the risk, whenever you are going to the penalty term, then risk with respect to W1, that is means that R1 region that you have to decide in favor of W1, then what are the risks? R1 is equal to lambda 1 1. So there is a no problem. So pattern actually belong to class 1, classified in class 1. That is absolutely okay. Then this is a risk, and this lambda, this is a penalty term that you are going to add. So you have to estimate it. Similarly, for the risk with respect to W2, that how we are going to have, that is a R2 is equal to lambda 2 1 px W2. So this is a for this wrongly classified in this other class, that is a W2. So that you have to calculate, and this is a probability of wrong decisions, and it is weighted by the penalty term. The average risk that you can calculate, R is equal to R1 PW1 then plus R2 into PW2. This is an average risk, so that you can calculate it. Now you have to choose this which region that you have to choose so that R is a minimized. Now then you have to assign X to, so your objective is to assign X to one of the classes where you are going to have this loss will be minimum. So now this L1, this loss will be calculated. This is L1. This is a lambda 1 on pxw1. We are simply using this base rule, but we are attaching some kind of penalty term. That's it. And which is for this L1, and this is an L2 if it is classified in L1 or it is classified in L2. Then equivalent to, you can assign X in W1 and W2 if it satisfies these two things. One is called alpha L12 means likelihood ratio. So it is nothing but the px W1 divided by px W2, and you just simply changing this operator, and you can have, this is a lambda 21 minus, I am using it, you just using these entire things and do some operation, then you can end up with this equation. This is a very simple equations. Okay, and this way your objective is to choose R1 and R2 in such a way so that your cost of the misclassification will be minimum. So if you are going to use some equiprobable classes, and where lambda 1 is equal to lambda 2, lambda 1 1 is equal to lambda 2 2 is equal to 0, and prior probability is equal to half, then your then you can have this X is belong to W1 if this condition is satisfied, because only you are going to consider lambda 2 1 and lambda 1 2, because this is a 0, and this is if lambda 2 1 is equal to lambda 1 2, then this is called this minimum classification error probability. So when this condition will arise, when you are going to have this equal weights of this error. So this is a very important part of this base decisions rule, and these were the derivation. Now in a nutshell, what is the base decisions rule? That P1 X1, P2 X2, PCX. So this is called this, that is a class conditional density function, or I can write it in a different way. That is, I can write Px given. So I can write in a other way also, that I can write instead of writing it, I can write this way. That is a probability of I can write x given C1, X given, this is a I can write this is a X given C1. So probability of X given C1, so this is a X, this is a vector. So probability of X given C1, that, and probability of X given C1 is, it is a nothing but is a P1 into X. So every time I am not going to use, just going to write this class, this class level. So P1 X and P2 X and PCX, then X is belong to Rn. So we have to calculate this class conditional probability density function. Then second step, there is a prior probabilities that are given P1, P2 till PC, and this prior probability, it is a nothing but, obviously it should be 0 to 1. Now prior probability, and for I is equal to 1 to C. Now for I is equal to 1 to C, Pi is equal to 1. Now you can choose, if I'm going to solve the C classes or two classes, then if I'm going to choose prior probability for the first class is 0.5, then obviously you have to choose the prior probability for the second class also 0.5. If you are going to choose prior probability for the first class is 0.3, then you have to choose the prior probability for the second class is 0.7. So, and if you are going to see classes, and if you just sum them all, the prior probability should be equal to 1, because this probability value should not be greater than 1. Now you put X in class I. So how this is the decisions rule. Now you put X in class I if capital Pi means this is a prior probability for the first class. If capital Pi multiply by small pix. So small pix means density function for the class I. If it is greater than or equal to capital Pj small pjx. Okay, for all j is not is equal to 1. So why I'm going to use the equality? Why I'm going to use the equality? So it may so happen that if there will be some conditions where the point will be on the line. Okay, so if your decision boundary that you are going to make, so if your classified point on the line, then you have to take a decision whether the points belong to class 1 or class 2. Then you can just take a arbitrary decisions, then that you can just put the point in the class 1 or put the point in the class 2. So that's why, so there is a possibility this, that is whenever you are going to have this equality, means that your decision boundary, I mean the point that is you are going to classify, it is on the line. So because both the probability values are equal. Now when both the probability values are equal, then at that time how you are going to take the decision? So ultimately your objective is to take the decision or to find this class belongingness of this pattern, in which class this pattern belongs to, whether it is a class 1 or in the class 2. So if it is strictly greater than 0, then that is the things that it will be either in the class 1 or in the class 2. But if it is going to make equal to sign, then so if the test pattern of this class on the line on the decision boundary, then it will just give some perturbation to move to this either class 1 or in the class 2. So this is this way, that is that we are going to using greater than is equal to, and for all j is not is equal to I, and you have to select the base decisions rule which minimize this probability of this misclassification. So this base rule is said to be a optimal. So base decisions rule is optimal. Why it is called optimal? Because it minimizes this classification of error probability. So that's why it is called the base decision rule, and it is called the best decisions rule, because you take any other classifications rule, any classification rule, then you can apply it, you can change it. Then this probability of the misclassifications rule, if you can prove it, that probability of the misclassifications rule for any other rule, if it is a less than of the base decisions rule, then that this rule will be a very good rule. So these are the examples. So I'm just stopping in 5 minutes. That these are the examples. That is a for you can just take as an assignment. That is a, for example, if px given w1. So this is a density function is given, and for the other class px w2, it is another density function, and pw1 is equal to pw2 is equal to half, because you are going to use equiprobable classes, and this is a loss function, that is a 0 0. So mean that is a all diagonal elements, that is a lambda 1 is equal to 0, lambda 2 is equal to 0. This is a correct classification, and 0 find. So this is an your lambda 1 2, and this is a lambda 2 1. Now you have to compute the threshold x naught for minimum error probability and for minimum risk if the loss matrix is given above in this way. Now if you just solve it, then your this threshold for this minimum probability case will be, that is x naught for this minimum. You have to calculate it. X naught is equal to exp of x square. Then you need to do that is exp of minus x minus square, and x naught is equal to half. That I can choose x naught is equal to half. Because why? Because you can take the logarithm on both sides. If you take the logarithm of both sides, we end up with x naught is equal to half. And in the minimum risk case, we get that you have to choose the threshold x naught. I mean x naught hat for this minimum of half. That is x naught is equal to, this is a 2 of exp of these things, and this one minus ln 2 by 2, and which is also less than of half. So that you can just prove it in this way. And if you just move this your x naught to the left of the half, then you are going to have these two different decision boundary. If you have this 0 and 1, Then if the two classes are not equiprobable classes, then it is easily verified that P of W1 is whether P of W1 is greater than P of W2 or P of W1 is less than of W2. And this threshold moves to the right to left if P of W1 is greater than P of W2, you just move to the right, or P of W1 is less than of P of W2, you just move to the left. So that is you can expand this region in which we decide in favor of the most probable classes, since it is a better to make the fewer errors for the most probable classes. And when the intersection between, actually it is a set, if you can have, it is a region, if the intersection between these two region is null, if there is no common element between the two set, then there is a 100% classification accuracy, because there is no common area region. But it is actually not possible indeed. So these are the application domain that is a for this supervised classification you can use as a machine vision application. These character recognitions, computers aided diagnosis, speech recognitions you can use, and it is used mostly in some, if you are going to have the data set with like this uncertainty is involved, or there is some problem is involved, then you can use this base classification technique. It is very good rule. And because why it is called the base decisions rule, because it has got a good mathematical justification. Okay, so any other rule or anything so that is very difficult to use, or this difficult to judge. So as the base decisions rule will have a very rich mathematical formulation or very rich mathematical way to understand, then this is said to be a base decisions rule. So thank you so much for your kind attention for the first session. So I'll take this 5 minutes break and I'll start the second session. But the meantime, if you have any questions, so you can directly ask me.
Hello, Anup sir.
Yes, sir.
There are some questions in the chat box. If possible, you can take a two or
Okay,
three
sir.
questions, sir.
Okay, sir. So how does the y data not come in this actually so you can also come this x1 y1 you can write it, but here we are going to use only single variables. I mean x1 x1 x2 x2 x1 x2 x1 x3 x1 x3 x1 x1 y1. So you can also take the x1 y1 also. No, there is a means no problem. Okay, you can have the x1 y1, you can have the x2 y2, you can x3 y3, so x and y, and so it is just a notational problem. So you can also use it. Okay, sometimes bar is the above x and sometimes x in below x. The same, So this the whenever I am going to using bar in x, it means it is a mean or average, and the formula is if you are going to have the n observation x1 to xn, then x bar it is a mean or average. It is 1 by n summation of I is equal to 1 to n xi, because you are summing this all the values and you have just divided it by the total number of values. That is called the average. But whenever I'm going to using x in the underline, it is a vector. So vector means it has got a, if you are going to have the n dimensional vector, it has got the small n components, means small n values, x1, x2, x3, xn. Suppose to make it more clear, suppose you are going to making a coin 10 times. You are just tossing a coin 10 times, and suppose for the first time you can get the head, in the second time you can get the tail. So you are going to have this 10 observation. So each observations are called, that is called the trials. For each trial, this is called the values. So what is the values? Whether it's a head, h is a value, and tail, t is a value. So this is called the component x1, x2, x3, x3. Okay, so could you kindly suggest some books that cover the fundamentals of uh, okay, could you suggest some books and that cover the fundamentals on both of the theory and application? Yes, so this very I'll just share this PPT, and you can see there's a books is already there of the fundamental of statistics. There's a very good book is called the Gun Gupta and Das Gupta. That is a fundamental of the statistics. Whatever that is being discussed, it is already there in the book itself. You can just check it. There's a Gun Gupta and Das Gupta book is there. fundamental of probability and the statistics. And for these pattern recognitions that I explained to you in the mathematical, there's a theoretics book is there, pattern recognition. This name of the book is theoretics. I'll share with Professor Surendra Hans the link of this book when this today's session is over. You can find its theoretical background also, all these things. Okay, so in slide 33, explain the equality case again when this error probability becomes. Okay, just let me just check in this 33. Okay, yes. So actually, it may so happen, it is written that P capital Py small Pix is greater than is equal to capital Pj small Pjx. Okay. So now in this equality means that if there is some cases where this class belongingness, I mean the probability value for the first class is equal to the probability values of the second class. If there is a situations, then there may be some situations where these both the classes, these probability values are equal. Now whenever you are going to have this type of situation, then you can arbitrarily put this x in any of the two classes. So there is a chances of that these conditions will appear. If these conditions is appear, these both the probabilities values, okay, of the both the classes are equal, then how we are going to take a decisions that whether this x is belong to class 1 or it's belong to the class 2. It means that this class belongingness, the belongingness of the x in the class 1, it will have the one probability. Belongingness of the x of the class 2, it is also give the another probability. And equality means when these both the probabilities are equal, then how are you going to take the decision? Then you need to put this x is any one of the two classes. So whenever this situation arises, it means this point is on the line. Okay, this is a decision boundary, and if the points on the decision boundary, this is on the line, then you have to put forcibly this point either one of the two classes. Then obviously there will also be, you have to estimate this error also at that time. So I think, sir, I am done for the first session. If anyone have any questions, you can post me in my email or other things. Surendra sir, is it okay?
Yes, sir. Yes, sir. Sir, everything is fine, sir. Now you may take a 5 minute break, sir, as per your convenience. Then next 1 hour that we will start.
Yes,
Uh,
sir. Sir, I'm just taking a 5 minutes break. I'll just sharply start at